Hello, good afternoon. Here we are for part 2 of lesson 2 of CENG 3325 structural analysis. Alright, in this video we're going to continue on with our discussion of determinacy and stability, and in particular we're going to be looking at stability and how to determine it mathematically. So let's look at stability. Make sure we're recording and we're rolling, and we are, so we're good. Okay. So let's consider stability. Stability here. And we already discussed it briefly in the last video, but I think I'll review a bit of it here. What do we mean when we say a frame is stable? Well, we have two forms of stability that we might consider, and these are going to be external stability and geometric stability. And geometric stability. So we have both external and geometric stability. And let's define each of these. So external stability, again, is going to be whether a frame or truss can resist translation or rotation. Frame or truss can resist translation or rotation. So this is a bit of a review from the previous portion. Translation/rotation. And geometric stability is whether a frame can retain its own geometry when under loading. Well, actually I should say whether a frame can retain its own geometry when removed from its supports. When removed from its supports. So for example here, let's go through a few examples of each of these. If I had say a simple truss, something like this, maybe something more like this. If I have a nice true truss, nice simply supported truss, this is something that would be, and I connect it with, say, if I support it just simply supported, I would have a externally stable truss. Same thing with a frame, a rigid frame, something like this. If I connect it with a pin and a roller, that would be externally stable. If I look at the reactions here, I would have my X reaction and my Y reaction, and my Y reaction here, X and Y, and of course my Y reaction here. And again, stability is going to be a property of the frame, of the geometry, not dependent on the loads. So we saw that last time. So key to keep in mind, stability is a property of the frame geometry, not the loads. It is independent of loading. Is dependent, or is a property of frame geometry and support, not the loads applied. It is independent of loads applied. Okay, but then let's look at some examples of geometric stability and geometric instability. So for something to be geometrically stable, when I remove it from its supports, the geometry itself must be able to maintain the shape of the object. So for example, consider this. Consider a simple frame here, a rigid frame. This frame is going to be geometrically stable. I have rigid supports here and here. So this is geometrically stable. If I were to trim this thing from its supports, if I were to come along with a saw here and cut off the supports here and here, and just have this, U-shaped piece of steel or concrete or whatever it is, and I lifted it up by a crane, maybe if I lifted this thing up by a crane at this corner, I would end up with something like this, hanging in the air like this. Its orientation would change if I'm just hanging it from a rope by this corner, but the actual shape of the object wouldn't change, assuming the rigid joints are truly rigid and treating this as a truly infinitely stiff joint, etc., etc. At least if the joints are strong enough to the point where we would consider them usually rigid. Of course, in a big building, if you tried to pick an entire building up off one corner, even if we define those joints as rigid, in reality, a building is not really designed to be picked up by one corner, so that probably wouldn't work too well. But anyway, that is still the basic definition of geometric stability. If you can remove this thing from its supports and lift it up or something like that, or just have it floating in the void of space or something like that, when it's removed from its supports, if it retained its shape, it will be geometrically stable. Let me show you an example of something that is not geometrically stable. Let's say I have a frame, a two-member frame, with a pin support, or sorry, a pin joint here, and maybe two pin joints here to support us. I'm getting lazy on my language. I have a pin joint in the middle here and two pin supports here and here. This frame is, as it's positioned here, is going to be able to resist any loads that are applied to it. If I pull on it this way, if I pull on it upward or to the right or to the left, if I pull down, if I apply a torque or a moment to this thing, it will be able to resist motion via the supports. But the frame itself is still geometrically unstable. If I come along and cut this thing here and here, and then lift it up, let's say I try to lift it up by that center pin, what I'll end up with is these things kind of collapsing in on each other like this. I'll end up get kind of a scissoring action, and I'll just end up the entire frame will end up collapsing and changing its geometry. So this frame here is intrinsically geometrically unstable. Geometrically unstable. So again, there are two types of stability. There is external stability, which is dependent on the supports, and geometric stability, which is dependent on the frame, independent of geometry. Now, how do we mathematically determine this? For simple frames, you can often just eyeball it. So for example, for that previous frame, the one on the right, we can just eyeball it and say this is clearly geometrically unstable. Frames can determine stability via inspection. You simply look at it and say, okay, you kind of imagine moving it in your mind and see, okay, well, it could pivot here, it could bend here, something like that, via inspection. But a better method is one that's mathematically determined. For more complex frames, we do have to use the mathematical tool. So for more complex frames, if I can manage to write the word more properly, for more complex frames, a relationship we can use is that if R is less than or equal to, is less than 3n, it's going to be geometrically unstable. And in turn, if R is greater than or equal to 3n, it will be geometrically stable. And what, again, in case you don't recall or haven't seen the previous video, R is going to be the number of reaction forces, including any internal forces revealed by cuts. And N is the number of pieces that you are dividing a frame into for analysis. Is divided into, actually, pieces frame is divided into for analysis. And I thought I would give one note on this whole division thing. After class, a student came up and asked me about this one particular case, and I think it is a good practice, and something I should probably note. When you're determining your number of supports, your number of pieces and your number of reactions, if there is any kind of internal pin present in a frame or something like that, so for example, say we had a, I don't know, like a frame, something like this, that kind of thing. Say I had a pin there, and maybe a fixed support, and I don't know, let's call a pin support here just for fun. By default, a good practice when determining both stability and determinacy, if I ever see a pin support, I generally just want to automatically cut it right there, because otherwise, I should say that the N doesn't just mean the number of pieces. What it really represents is the number of rigid bodies that you're considering during your analysis. And something with a pin inside really can't be a single rigid body. So if you ever have a pin, you'll want to automatically separate that and treat this as one piece and this as one piece at a minimum. You can still divide it up into more pieces if you like, but really I need at a minimum, if I ever see a pin, I want to immediately split it up into two different pieces. So in order to determine stability and determinacy, I would analyze it as this piece here and this piece here. And let's say my reactions. Well, if I look at my reactions, I would have, I could draw them out, but I think I'll just, well, yeah, let's go ahead and draw them out. X, Y, and a moment. X, Y, and a moment. Again, equal and opposite. And then just an X and a Y here. X and a Y there. So in this case, what I would say is N is equal to 2, and what else? I would say R is equal to 3 plus 3 plus 2. So that would be R is equal to 8. 3 plus 3 plus 2, 3 plus 3 is 6, plus 2 is 8. So would this be unstable or, let's see, would this be geometrically unstable or stable? Well, R is indeed greater than or equal to 3n. 3 times n is 6. 8 is greater than 6. So this would actually be geometrically stable. Alright, so looking at this, we see that our mathematics indicates that this is geometrically stable. However, can you see a problem with this? Yes, the math shows this is geometrically stable. However, there is one important caveat and exception to this equation. Exception to the Rn equation of geometric stability. If there are concurrent forces or coplanar forces, concurrent / coplanar forces, or an obvious collapse mechanism, the Rn equation may not be valid. The Rn equation is not the full picture. May be invalid. Or in other words, those only apply when there is not an obvious collapse mechanism or coplanar forces. So for example, I was trying to apply the R equals 3n here, but we saw, but just looking at the frame though, I can see that there is something very wrong with that. So for example, I applied them correctly, but when you look at that frame, there is a clear collapse mechanism. So the moment I retract this thing or cut this thing from its supports, I don't care what the math tells me. I know this end of it, when this thing is flying through the air, if I cut it at the support here and cut it at the support here and pull it up by one of the ends, say I pull it up by this end here, what I'm going to end up with is something like this. One piece will be, the left piece might be hanging like this, if I pull it up via a cord there, and instead of being nice and level, maybe this thing ends up bent over like this or something. Well, it'd still retain the right angle, the fixed joint, but I'd have the pin here, and maybe this thing would be hanging, oh, I don't know, something like that. Definitely bent over at an angle of some sort. So this is a case where the R and 3n, R is less than 3n, R is greater than or equal to 3n, equations don't apply. Simply because if there is a clear geometric instability in the frame, or when there is a clear collapse mechanism, for example, an internal pin like this, that will serve as a source of geometric instability all on its own. Let's see, other notes on this, other things to keep in mind. Also, just like we did previously, be sure to cut any closed loops, just like we did with determinacy. So you want to be sure to cut any closed loops. So I also want to look at some other sources of instability. So let's look at some other sources of instability. Other sources of instability. We have a few. And we've already alluded to them before. These come from coplanar or parallel reaction forces. So in other words, let's see here. If you have reaction forces, I can just state it here, if reaction forces act along the same line of action, or are parallel, you can get external instability. Can/will have external instability. A frame can still be geometrically stable, but if you have your reactions misaligned, essentially, you'll end up with external instability. Can/will have an externally unstable frame. So for example, imagine you have a frame like this. Let's say I have a frame with, 3 rollers would be a great example. Or we could actually make it extra fun and have 4 rollers. Doesn't really matter in this particular case. Imagine I have 4 rollers aligned on a perpendicular frame. So a sort of cruciform frame here. Like this. And let's look at our reaction forces. Let's say I have reaction forces here, 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 and here. If I try to pull this thing to the left or to the right, this force and this force will balance that out. If I try to pull it up or down, these two forces will resist that. But the moment I try to rotate this, nothing here will be able to resist that. So at the moment I try to rotate this, none of these forces will be able to resist that rotation. And the reason I know that is there is a point that I can sum moments that none of these forces will generate a moment about. If I sum moments about the center here, there will be no moment produced by either of these forces. Therefore, if I have a couple, say, applied at the center, I know that there will be nothing to resist that, and this frame will go into motion. So again, if I define this point as A, if I can write the letter A better, when I sum moments about A, I get 0. So therefore, no force to resist a moment applied about A. No reaction forces, I should say. Oh, force, lovely. No reaction force to resist moments at A. And this thing will just start rotating. Another example would be perpendicular forces, parallel forces. And there are also parallel forces or parallel supports. And this is another case where you can have external instability. So parallel supports imagine if I had a large frame with a series of rollers on it, like this. Well, in this case, all of my reactions would be pointing vertically. So I could have a reaction, here, 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 and here. But if I try to sum forces vertically, if I try to pull this thing vertically, it'll be fine. If I try to do a sum of moments somewhere, if I try to apply a moment to this thing will have abundant capacity to resist moment about basically any point. But the moment I try to apply a horizontal force to this, it will not be able to resist a horizontal force. So this thing is just gonna roll away. I can, if I want to, or if somebody wants to, they can come along, hitch a truck to this thing, tow it away, and sell it by the pound. So this frame here is good for vertical forces. It's good for moment, but it's not good for horizontal forces. And we could design frames, or we could draw frames that would be good for any number of these. Like or for any combination of these. So, for example, we can have one that's good for horizontal force and vertical, but not moment. That's this one. We could draw one that's good for moment and horizontal, but not vertical. We can come up with frames that are good for any combination of these, leaving one of them out if we're particularly creative. Now, in turn, we have a way of classifying frames as basic according to stability. So let me define how we classify frames by stability. Just like we had degrees of instability, we'll have ways of describing how frames are externally constrained. So let's talk about constrainment or external stability classification. Constrainment and external stability classification. You may remember this from statics class, but it would be good to repeat this here. Broadly, we classify frames as three ways. One, properly constrained. So here, A, there will be greater than or equal to 3 external reactions, or let me just say at least 3 external reactions. At least 3 external reactions are present. And B, reaction forces are not all parallel or do not all point through act through the same line of action or act through the same point. So reaction forces are not all, maybe I can do this in IJ form or something like that, not IJ, outline form. 1, or maybe I, are not all parallel. 2, do not have lines of action that all pass to the same point. That all pass through the same point. And that is what we have. That is what you're going to have for a properly constrained frame. Here, to our second way of looking at it, our second classification, we can have partially constrained frames. Here, you would basically have, or you would need to have less than 3 external reactions. Less than 3. External reactions, and if you don't have 3, if you don't have at least 3, there is always going to be some external force you can't resist. Because of this, cannot resist one or more of X translation, Y translation, or rotation. And then 3, the third classification, would be improperly constrained. Here, you actually do have the requisite number of restraints. You have greater than or equal to 3 external reactions. greater than or equal to 3 external reactions, but B, you have something that makes it externally unstable by the layout of the reactions. Layout of reactions. The layout of the reactions produces external instability. As we discussed previously, this means things like parallel reactions, coincident reactions, coinciding reactions, etc. So let me give some examples of each of these three. I'll do this in a different color, maybe orange for fun. So let's look at this here. If I were to have a properly constrained frame, maybe an example would be something like this. Nice simple pin-pin form here. I would have 4 reactions here, very nice and simple. X, Y, X, Y, that would easily be able to resist translation in 2 directions, and rotation, very simple. I could have a simply supported beam. I could have something like this, just a nice simply supported beam. That might be as close as you can get to it. That might be the simplest way you could get a properly constrained beam. I could end up with something with lots of stability, with just an incredible amount of stability. If I wanted to look at a beam, imagine a fixed beam. That would be externally stable. Has more than enough, has twice as many things as it needs to resist all 3 forces, all 3 modes of movement, all 3 degrees of freedom is what I want to get at. I could also have something a little simpler. I could just have a cantilevered beam. Imagine I had a cantilevered beam just like this. And this could be either vertical or horizontal. This thing will be able to resist both translation, X and Y, and moment just because of the fixed support there. By default, really, anything with a fixed support is going to be externally stable. It may not be geometrically stable, but by definition, anything with a fixed support is going to be externally stable. Then, partially constrained is going to be really easy. All you got to do is look for ones that don't have, all you're looking for is frames that don't have at least 2 reaction forces. So if you had, I don't know, if you had a beam that had a roller and a roller, that would be an example of a partially constrained frame. Or if you had a, I don't know, it's hard to think of something that's, well, I guess I could have a truss or something, or just a frame like this. Imagine I have a frame with a roller and a roller. That would be partially constrained, or I could have a beam. Let's look at that pencil condition that we talked about previously. So I have a pin support here and just a beam, or sorry, in this case a column, coming up from that. All of these would be partially constrained reactions. Or I could even have an extreme condition, the rope condition, where imagine if I had a ceiling and there's a roller support here. This is basically a rope hanging from the ceiling. And in this case, I have only 1 reaction, and that is extremely partially constrained. And it would only have 1 restraint. So this would be capable of resisting up and down force, but it would not be capable of resisting lateral force, and it would not be capable of resisting any kind of moment. And then 3, improperly constrained, we've already discussed these. This would be things like the parallel rollers, like this, where they're not going to be able to resist forces in the horizontal direction, or the kind of system we would have here, where the 3 rollers, all their reaction forces pass through the same point. Each of those would be improperly constrained frames, in the sense that you do have enough forces, if deployed properly, to really completely immobilize the frame, but you just don't have them properly laid out. As a final note on constraint here and stability, final note on stability. Let me get this here, some final notes on stability. Stability and determinacy can exist in any combination. Can can exist in any combination. Now, very often, statically indeterminate frames are going to be stable. That's fairly typical. But you can have any combination you like, just depending on how the frame is laid out. If you gave me a set, like if you told me, draw a determinate frame that is unstable or something like that, or a partially constrained frame that is, well, I guess you couldn't have all combinations. I don't think you could have it's difficult to imagine how you would have a statically determinate frame that is say, unstable, statically determinate frame that is unstable. That would be difficult. Or, well, actually, no, that should be fine. I'm thinking a partially constrained frame that is statically indeterminate. That would be very difficult. There might be some way to do that if I sat down with a pen and paper and tried to really rack my brain. There might be a way to do that, but that'd be very difficult to do. But anyway, these can exist in any combinations. It's almost like there's category A and then category B. So you have column A and column B. You have determinate and indeterminate. And then you have your various stabilities. You have geometric stability. Well, actually, you can almost have 3 columns. You have geometrically stable, geometrically stable, geometrically unstable, just abbreviating here. And then you could have your external stability, which is really your constraints. So you could have properly, so then column C, properly constrained, partially constrained, and improperly constrained. And really, frames can be classified according to these 3 criteria. And it's really just to pick one from each column. So something can't be both geometrically stable and geometrically unstable. It can't be determinate and indeterminate. You have to pick one from each column. But you can pick whatever you want from each column, or maybe not pick whatever you want, but a frame can end up with almost any combination of these, maybe with a few exceptions, but generally you can end up with almost any combination. All right, that'll do it for today, for this lecture. Thank you for watching, and as always, thank you.